All right, this is MA 161's Spring 2020 Exam 1. This was like, I think, the last or the second to last exam that the math department gave right before the COVID shutdowns happened. That was like in mid-March or something. They might have given out midterm too by that point. But uh, this was right before all the lockdowns, and I was planning to do fall 2020's exam one instead, but when I pulled up the PDF, it was instead of, looking like this, where it had like, it actually looked like a piece of paper that they would give you. It was really just a screen grab of like a website because I guess that's how they gave out the exams during COVID, during all the online stuff. So there wasn't a whole lot of room for me to write out all my work. All the problems were still good. In fact, it was newer, so it was probably a little bit better of study practice, but um, again, I couldn't really work out anything, so I'm doing this one instead. And by the way, even though I just said that newer exams are better, these topics have not really changed at all in the past like 10 or 15 years. So even though I think these exams are going to date back all the way to 2016, those ones are going to look the exact same as what you're going to find on your midterms in 2023 and beyond. So um, you'll have a lot of relevant study material after I'm all done with this. So, exam or not exam one, question one. It is not a domain problem, surprisingly. It's just asking us to simplify these two fractions and put them into one fraction. So, when you're trying to combine two fractions, you need to have common denominators. You need these two denominators to be the same thing, and you can achieve that. Sorry, excuse me. You can achieve that by multiplying different things on the tops and bottoms in order to get the denominators, the bottoms, to be the same on either side, and then you can go ahead and add them. So I think the easiest way to go about doing that, instead of just like, multiply this side by z squared minus 49 over z squared minus 49, and then, the other thing on the other side. Instead of doing that, which I don't think would actually be simplified at all, we can realize that both of these denominators are really easily factorable. So it looks like the left side is just a standard quadratic equation where it's ax squared plus bx plus c. And on the right side, it's a difference of squares. So you can easily factor that one too. So let's go ahead and write out what I just said. So this left one here, z squared plus 14z plus 49, I believe this is going to factor out to z plus 7 squared. I'm actually going to expand that out to z plus 7 times z plus 7. If you were to FOIL this back out, if you were to multiply these two terms together, you would get back to that. So they are the same thing. And then this is all over 3 and then plus on the, so now we're looking at this. This is a difference of squares because it's two perfect squares that are being subtracted. So to factor this, it's just the first term's square root plus the second term's square root, and then the first term's square root minus the second term's square root. So it's all that, then we've got the top, and now we can see that both terms have a, I'm sorry, these z's kind of look like 2's. I should make that a little more clear. Um, both denominators have a z plus 7 in them, so that's one less term that you have to multiply out to everything. It looks like we can just multiply both sides by, I'm going to guess we can do z minus 7 on this side, or z minus 7 over z minus 7. And on the right side, we can multiply this fraction by z plus 7 over z plus 7. So now that we have this, you'll see that the left side denominator will have z minus 7, z plus 7, z plus 7. And on the right side, we're going to have z minus 7, z plus 7, and z plus 7. So it all checks out. We will end up having the same terms on both sides. So then when we go ahead and add them, they have common denominators, and we can just add the two numerators together. So doing this, we will get, I need to kind of flip my laptop around because this is getting hard to do while it's like in a regular laptop mode. This is going to be 3 times z minus 7 all over. I'm just going to keep everything like written out and expanded. So z minus 7, z plus 7, z plus 7 plus 2 times z plus 7 all over z plus 7, z minus 7, z plus 7. So these two numerators, or sorry, these two denominators are now the same. So we can go ahead and add these two fractions. We can just add the two numerators together. So we'll get 3 times z minus 7 plus, actually no, I think it's a good idea if we were to multiply these numerators out at least. So the top would become 3z minus 21, and the right would become 2z plus 14. And now we can add these a little easier. So this will become 3z plus 2z equals 5z. A little more on the left, 5z. Minus 21 plus 14 is minus 7 all over. This will, common denominators, you just rewrite one of them. Z minus 7, z plus 7, z plus 7. So now we're here, and it looks like our answer, well, it's not going to be D or E because they have 5z, plus 7 on the tops there. Looks like it's going to be, if we were to rewrite this actually as 5z minus 7 times z minus 7 times z plus 7 squared, that's going to be B. So, just a simplification problem, calling back to the factoring tricks that you used in algebra. We had a difference of squares here, where you just pull them apart and their square roots, and then you had just a standard quadratic equation down there, where you can separate it into the same term being squared, and then just simplifying from there, combining like terms, and eventually getting this fraction down to just one fraction. All right, question 2. Find the domain of f of x here, this square root of 1 minus ln of x. So, all right, so recap on what domains are. Domains are just the range of values that you can plug into the x in the function that will still make the output of the function valid. So what that means is, like, if we had a simpler function that was like g of x equals the square root of x, you've probably heard before that you can't take the square root of a negative number, or else you get like an imaginary number. So I'm talking about things like that. There are some values for this function that we cannot plug into it, or else we get an imaginary number, or it's undefined or something. So in this case, the domain, let's see, it goes from 0 all the way to positive infinity. So you'll see we kind of just cut off all of the negative numbers. We're saying that x can only go up from 0. So that's what I mean by domains. There's a couple of different things in math that can cause restrictions on the domain. There's usually 3 that they like to test you about. The first one, the one I just said, is where you have a square root. The inside, it can't be negative. You can't take the square root of a negative number, at least not this early on in calculus. So we know x must be greater than or equal to 0. Another common one is fractions. So when you have some kind of fraction, the denominator, it must not be equal to 0. You can't divide by 0. And then another one, it looks like it's going to come into play in this problem. It's a little rarer, but it's whenever you have logarithms. So when you take the logarithm of x, x must be positive. It must be greater than 0. It can't be negative, and it can't be 0. So those are the big 3 that they like to throw at you for these domain problems. So we're going to, looks like we're going to use these 2 for this one. Usually we've got like 2 or 3 in each of these problems. We've got 2 here. We've got this square root, and we've got this log base e of x. That's what ln is. So you can go about them in any order you like. I just kind of prefer to start inwards and then work out. So I'm going to start with this inside ln x here. We've said before that whatever's on the inside of that log must be greater than 0. So we know that this x must be greater than 0. So in this case, usually for these restrictions, you'd have to do some algebra and some like subtracting and adding on things on both sides to get x all by itself, but in this case x is already by itself, so we don't have to do any extra work. We've got our first restriction, which is x must be greater than 0. And now, actually I probably should have left that up there. And now for our second one, we have our square root here. Now we said earlier that whatever's inside the square root must be greater than or equal to 0. So whatever's inside the square root, which is 1 minus ln x, must be greater than or equal to 0. So now we just solve this for x. We put it on one side. So it looks like we can subtract 1 on both sides to get negative ln x greater than or equal to negative 1. We can multiply both sides by negative 1, and we'll get x is, okay, this is important for these inequality questions. So, as we just did, we multiplied both sides by a negative number. We multiplied both sides by a negative 1 to sort of flip these signs. Whenever you do that, you have to flip the sign of the inequality around. So this greater than is going to become a less than instead. So when you multiply or divide by a negative number, you have to flip the sign of the inequality. So now we have x, or actually ln of x, is less than or equal to positive 1. Now to get rid of this ln of x, what we can do is we can put e's down here. So this function is now e to the ln x is less than or equal to e to the 1. What this does actually is on the left here, this will get rid of the e and the ln, and we're just going to be left with x. So this is going to become x is less than or equal to e. So that is our second restriction. Whoop, I messed that up. X is less than or equal to e. Looks like that's all the ones we have to worry about, and we can just go ahead and turn these into, the proper domain notation, which it looks like B is the one, since look what it's saying. It goes up from 0 exclusive, so that means it doesn't include the 0. Oh my god, just dropped my pen. Whoops. All right, where was I? It goes up from 0 and does not include 0. That's what we said over here. It is greater than 0 and cannot be equal to 0. And then it also says it goes down from e inclusive. So that's what we said on the right here. X must be less than or equal to e. So definitely looks like B is the right answer here. All of the other answer choices are just small variations of that are just slightly wrong. Like it looks like if we were to just look at A, for example, it was correct on the right side here. It goes down from E inclusive, but it unfortunately went all the way down to negative infinity, which can't happen because that includes numbers like negative 1 and negative 2, and every negative number, which we said can't happen. X must be greater than 0. So that's the common theme from all these other domains. They usually just include numbers in their domains that we excluded from the correct domain. So we know that B is our right answer. Okay, question 3. This is one of those functions within functions problems. So usually how these go is they give you a couple functions it defines for you, and then it asks you to put them like into each other. So in this case, it asks for f of g and g of f. So this first one means you rewrite f, but with g as the x, and the second one means you rewrite g, but with f as the x. That's kind of confusing, but it's not so bad when you actually go ahead and do it. So to find both of these, let's see. Let's do f of g first. So what I said is you rewrite f, which is 4 over x minus 1, but you replace the x with what g is, which is 2x. So you rewrite the x, but with 2x instead. So that's f of g, fog, even though that's not an O, that's a circle, but I digress. Now we can go ahead and find g of f, which is the other way around. So we rewrite g first, we write 2x, and then we can go ahead and replace the x with f, which is 4 over x minus 1. So we replace the f, no, I'm getting confused. We replace the x with f, which is 4 over x minus 1. This gets kind of confusing sometimes. All right, so now we have our f of g and our g of f. Now I think all we have to do is set them equal to each other. So we set them equal to each other, and then we solve for x, because there's only going to be one variable, and we can just solve for it, and then we'll get our answers. So, all right, set them equal to each other. So we get 4 over 2x minus 1 equals, I'm going to write this as 8 over x minus 1. And it looks like to solve this to start, we can just cross multiply. So we multiply both sides by x minus 1, which will get rid of all of that. And then we can multiply both sides by 2x minus 1, which will do the same thing but for this term down there. So doing that, we will get, all right, multiplying both sides. I'm going to do this one step at a time. So we multiply both sides by x minus 1. We get 4 times x minus 1 all over 2x minus 1 equals 8. And then we can go ahead and multiply both sides by 2x minus 1 to get it out of the denominator there. We get 4 times x minus 1 equals 8 times 2x minus 1. So there we go. Now that we don't have any fractions anymore, I think instead of having these big terms here, we could just expand. We can just distribute everything to get 4x minus 4 equals 16x minus 8. And now we can, let's see, if we wanted to put all the x's on the left side here, we'd subtract 16x from both sides. So we get negative 12x. And we'd add 4 on both sides. This is minus 4. We divide both sides by negative 12. We get x equals 1/3. So, yeah, functions within functions problems. You always kind of work left to right, I suppose. You just write the function that's on the left and then replace all of its x's with the functions on the right. Now, sometimes you'll be asked to do like 3 functions in a row, where you have like f of g of h or something. But it's still the same logic. You'd rewrite f and then replace f's x's with g, and then you replace g's x's with h. So that's how something like that would work out. But in this case, it was just 2 singleton, like 2 of these, 2 by functions or whatever you'd call it. So it wasn't that bad here. We just had to set them equal to each other and then solve for x at the end. All right, question 4. How can the graph of y equals 6 times the quantity of x plus 5 squared plus 2 be obtained from the graph of y equals x squared? All right, this is a transformations problem. So it's like asking you, so if you start out with x squared, what transformations can you apply to it and in what order to get this? So for transformations, they always act inward and then go outwards. So in order to get it to look like this, it looks like the first thing we'd do is we would add 5 on the inside. So it looks like this would become x plus 5 squared instead. And what that does is when you add 5 on the inside, usually like on the inside of this squared here, maybe sometimes x is like an exponent and you put plus 5 in the exponent. Whenever it's on the inside like that, it's always horizontal. And since it's a plus, it means we're moving left. So what this means is we move left 5 units. I'm not even going to write units. We'll just put left 5. So now we have that. Looks like their next course of action is this 6 out here. Looks like it multiplies the whole thing by 6. So this is now 6 times x plus 5 squared. Since this 6 is on the outside of the square, it means it's acting vertically. Usually things on the outside act vertically. Actually, no, not sometimes, always. When you have things that are on the outside of the square or outside of the exponent or whatever it is, it's vertical. So this is going to stretch it vertically by a factor of 6. So stretch vertically by a factor of 6. And then the last step is this plus 2. So 6 times x plus 5 squared plus 2. This is simpler. Again, since it's on the outside, it's going to be vertical. And since it's a plus, it's going to go up. So it's going to shift it up 5 units. So these, transformations that we've done at it are E. Shift it left 5 units, shift it vertically 6 by a factor of 6, and then shift it up 2 units. So that's exactly what we've done by applying all of these transformations onto x squared. Question 5, and this is a different kind of inverses problem. Which of the following does not have an inverse function? So usually you're given a function and asked to find its inverse, but in this case you've got 5 of them, and it's like Russian roulette. One of them will not have an inverse. You can't do it. So, all right, an easy way of figuring out if a function has an inverse is by using the horizontal line test. So that might have triggered some alarm bells. Usually you hear and you use the vertical line test to see if something is a function. Like if you had something that looked like this, you could use the vertical line test to tell that, oh yeah, this is not a function because if you draw a vertical line right through its center, passes through it at multiple points. So yeah, something like this is not a function. Now what we can use for this problem to tell if something has an inverse is the horizontal line test. Or if we draw something out like a sine wave, we can use a horizontal line to tell, yeah, it intersects at multiple different points. So we know that a sine wave function does not have an inverse. So we can use that to our advantage here to tell what has inverses and what doesn't. Now, I just said that a sine wave, something like this, or a cosine wave, will usually fail the horizontal line test every single time because it passes through it at multiple different points. So you'd probably look at A and think, oh yeah, that absolutely violates it. It's just a sine of x, which just repeats on and on forever in a big wave. But look at its domain. Look how it is defined. It is the values from x between negative a half and positive a half. And when you graph that out, you'll see that it actually does not violate the horizontal line test. If you were to do this, so it would be something like, all right, right in the middle, when x is 0, it would equal 0. When you plug in 0 into sine, you'll get back 0. And when you plug in two endpoints, which is pi over 2, which is its maximum, when you plug in pi over 2 into sine, you get 1. So it'll be something like this, where that's 1. This is pi over 2. I think it'll grow like that in between. And then the other way around for negative pi over 2. So on the other side, it's going to be negative pi over 2, and it's going to equal negative 1. It's going to be something like that. Now you'll see this does pass the horizontal line test. No matter what horizontal line we draw, it's only going to intersect at one point each time. So since this passes the horizontal line test, it does have an inverse. So A is wrong. We're looking for one that doesn't. Now looking at B, this one I definitely think it's going to have an inverse. We can just go ahead and brute force this really quick. We replace the y's with x's and the x's with y's. We will get x equals y cubed plus 2. Solving for y now, we'll get x minus 2 equals y cubed, and the cubed root of x minus 2 equals y. So yeah, this absolutely does have an inverse because we were able to get y all by itself on one side. So B has an inverse. Now what about C? We could probably do that same trick again, try to see if we can get the y all by itself, and if we can't, it doesn't have an inverse. So this will become x equals y over y squared plus 1. This is already kind of raising some red flags because these are notoriously difficult, if not impossible, to get y all by itself because it's in a fraction and one of the either the top or the bottom, the numerator of or the denominator of the fraction has a constant that's being added to it. That makes things a lot more difficult to find the value of y for. So we can still try nonetheless. Maybe we can multiply both sides by the denominator by y squared plus 1. So we can get x times y squared plus 1 equals y. We can multiply the x out, maybe. We'll get xy squared plus x equals y. Maybe we can subtract the y, subtract the x. We get xy squared minus y equals negative x. I don't know how we get rid of this x here. That's kind of what I was saying. These problems are very hard, sometimes impossible to simplify and solve for y here. So I'm gonna make the call that this is the culprit. This is the one function here that does not have an inverse. So I'm gonna put a question mark here, and we'll run through D and E and maybe rule those out before we confidently say C. And I guess maybe at the end of this, I'll pull up Desmos and graph this out, see if it has if it passes the horizontal line test. All right, so now looking at D, y equals 1/2 e to the x. This one is looking more promising. To take the inverse of, we get x equals 1/2 e to the x, or no, not e to the x, e to the y now. We can multiply both sides by 2 to get rid of the half. 2x equals e to the y. And now we can take ln of both sides to get y all by itself. So this is ln of 2x equals y. So yeah, this absolutely does have an inverse, so D is wrong. What about E now? Okay, an ln function, that's different. The minus 2 here usually, that doesn't mean anything. It just means it moves to the right by 2 units, and that doesn't affect if it has an inverse or not. It's just shifting it in a different direction. So we can just ignore that. We can just kind of imagine this as an ln of x. And what that looks like, well, if that's just a logarithm. Logarithms go like this, and they kind of just go up forever, but also plateau like that. And yeah, this passes the horizontal line test because it ends right here. It doesn't go like down like that or anything like a square root kind of does. This just passes every point like that. It only intersects at one point each time. So it does pass the horizontal line test. So E is wrong. We can pretty confidently say that C is the one that does not have an inverse. And what I promised at the beginning, we can go ahead and graph this on a Desmos. I know you obviously can't have your laptop or your phone out during these exams, but still worth looking at nonetheless. So if we do desmos.com/calculator, we can do x over x squared plus 1. Oh yeah, so this does not pass the horizontal line test because you'll see, sort of like right here, if we were to draw a line of, let's see, y equals a half, no, y equals a fourth, it passes at 2 points. It passes right here, and it passes right here. So since it passes at 2 different points, it does not pass the horizontal line test, so C is correct. C does not have an inverse. All right, question 6. All right, this is a little more of a typical inverse question, as compared to the last one. It's one of those where it gives you a function, a definition of a function, and then asks you to find its inverse. And this is doubly cool because we don't even have to plug in a value at the end of it. Sometimes it usually asks you to plug in like 5 or 2 or 1 at the end of it, but we don't have to do that. We just find the inverse, and that's the answer. So finding inverses, again, you just replace the f of x with a y, rewrite it with a y instead. That's, life's biggest question, why? And then you flip the positions of all of the x's and the y's. So this one y becomes an x, and these two x's become y, so 6y and 2y. And now what we do is we solve for y. So when we solve for y, we'll get y all by itself on one side, and then whatever we have on the right here, that's going to be our inverse. So f inverse of x. So that's how we find inverses. Now actually going about and doing it, finding and solving for y. Let's see. I think a good first step is multiplying both sides by the denominator of that fraction. So we multiply both sides by 2x plus, or 2y plus 9. 2y plus 9. And that equals 6y minus 1, the numerator. Let's probably distribute this x and multiply it out. So this is now 2xy plus 9x equals 6y minus 1. Let's go ahead and subtract 6y from both sides. We're going to try to get all of the y terms on one side. So this is 2xy plus 9x minus 6y equals negative 1. Now let's try to get all of the non-y terms on the other side. So this will now be 2xy minus 6y. We can go ahead and subtract 9x from both sides. This is now negative 9x minus 1. Now we can take a y out from the left side. So this is y times 2x minus 6 equals negative 9x minus 1. And then divide both sides by 2x minus 6. So this is now y equals negative 9x minus 1 over 2x minus 6. There we go. So yeah, typical inverses problem, where you rewrite it with a y, and then not subtract, you flip the positions of the x's and the y's, then solve for y, and then what's left is your inverse. Not too bad. Question 7. This is my third time recording this question. This question keeps tripping me up, but it's not really that hard. It's kind of just a unit circle question, like testing your knowledge of the unit circle and knowing what angle values correspond to what output values for the given, the core two trig functions, sine and cosine. So at the core of it, it's just a solve for x problem. What x values here satisfy the equation? Immediately, I'm kind of worried about why it's not using theta for this, because usually you put thetas inside trig functions, because theta usually, corresponds to like arc lengths, which is what you put into trig functions, but it's whatever. They're just variables at the end of the day. And also, since these are, trig functions, these are sine waves, really, which look like this. So there's going to be an infinite number of x values that correspond to the same y value for all of it. So I think we're actually going to have an infinite number of answers here, but the test makers were wise and restricted it to just the x values between 0 and 2 pi. So that's just what we're going to do. Now to actually solve this thing, what values of x satisfy it? I think the first thing we could do is see that both of these terms have a cosine in it. So we could probably just factor out the cosine, bring it out front, and we'll have that instead. So we now have cosine x times 2 sine x plus 1 equals 0. And now what we can do is, since this whole thing, like these two terms being multiplied, since it all equals 0, we can just set both of them equal to 0, into two separate equations, and then solve them independently. So we can set cosine x equal to 0, and we could set 2 sine x plus 1 equal to 0. And we can just solve each of them by themselves, like independently, and their collected answers are going to be the full answer. It's going to be one of these when you put all of the answers together. So doing this, we just have two equations to solve now. I'm going to do the right one first because it's the one that has kept messing me up this whole time because I keep forgetting my unit circle values. So I want to get it down first before I don't mess up another one. So 2 sine x plus 1 equals 0. We should probably get this sine x all by itself. So if we subtract 1 from both sides, we get 2 sine x equals negative 1. Then divide 2 on both sides, sine x equals negative 1/2. All right, so what angle value makes the output of a sine equal negative 1/2? Well, I'm going to use this table that I actually learned way back in pre-calc that I haven't showed you guys yet, but is pretty useful for this problem. So I'm going to make a table with a sine and a cosine. Those are the two main ones. If you want to find like tangents, you just put the sine over the cosine. And then there's going to be 3 columns. So there's 3 columns. On the top here, we're going to put the 3 common angle values that aren't just multiples of pi over 2. So we're going to put pi over 6, pi over 4, and pi over 3. Pi over 2 and pi and 3 pi over 2 and so on and so forth. Those ones aren't too bad to solve. In fact, I think that's what the answer of this is going to be. So we're going to do that last. But for these less common angle values, which gives answers of like, a half and weird fractions and stuff, we're going to use this table. So if you want to find the output of certain trig functions and their inputs, you can just use 1, 2, 3, 3, 2, 1, square root them all, and then divide them all by 2. Divide by 2, divide by 2, divide by 2. And, I mean, root 1 is just 1. So, there we go. That is the outputs, the 6 outputs for these 2 trig functions and 3 input arc lengths. So if you wanted to find the cosine of pi over 3, it's a half. So that's pretty quick. You have to do a little more work if it's like a negative answer. You're trying to find something that's negative, which we are going to have to do here, but it's still not the worst thing ever. So since this is negative a half, we're just going to take the answer for regular a half, which is pi over 3, and we are going to, no, oops, I looked at the cosine instead. We have a sine, and we have something that is a half. It's a negative a half, but it's still pretty similar. As you get this, so now we're going to take pi over 6, and we are going to add pi, since it's negative. So this is going to become 7 pi over 6. Now, that is only one of our answers. I'm actually kind of blanking at the moment on how we'd find the second one. Come on, I can't mess this one up again. Come on. All right, unit circles like this. Oh, I see now. Okay, so the definition of the unit circle is just figuring out the length of, different lines that trace back to the axes from different arc lengths. So if you have an arc length that looks like this, what a sine is going to do, it's just going to figure out the length of this line. It's going to figure out the length of that line there. And you can see why there's usually 2 of them, because like that angle works and also this one too. These are going to be the same line length. So what I've actually done is this first angle that I've drawn here, it's actually pretty close to 7 pi over 6, which is pi over 6 plus pi. So that's why I did the plus pi back there. Now, if we want to find this other one, which is right here, it looks like we take 0 and then subtract pi over 6. We start at 0 and then go backwards. We subtract pi over 6. But since we can't have values that are less than 0, we can just take 2 pi and then minus pi over 6. So 2 pi minus pi over 6, that's the same as 12 pi over 6 minus pi over 6, which equals 11 pi over 6. That was a little confusing to figure out those unit circle values, but I hope you're just comfortable with it nonetheless, because I think that's something they teach you like in Algebra 2 in trigonometry, which was before, calculus and everything. So I hope this is just another reinforcement. But in any case, that's how I would try to find this one instead. Now, going back to the other one where we have cosine x equals 0, we go back to our unit circle, which is, 0, pi over 2, pi, yada, yada. Cosine is the horizontal value. So it's this length here for a given arc length. Now, if we want that arc length to be 0, we don't want it to be anything, that arc length has to just start and stop right on the y-axis there. So we need our angle to be either that or that, in which case it has to be either pi over 2 or 3 pi over 2. So those are our 2 answers here, pi over 2 and 3 pi over 2. So we now have our 4 answers, and it looks like C is the correct answer here. So, okay, I think that was a decent enough explanation of unit circles. Again, you might already be comfortable with this after some of like high school stuff. But if you're not, I hope this was a decent enough intro to it. If you really want to practice more, you can just Google unit circles, and there'll be a whole bunch of awesome YouTube videos about it. But this question was a decent test of all those unit circle properties. All right, question 8. How many of these following statements are true? Okay, that's kind of weird. Usually it's like you find out which ones are true, and then it'll be like 2 and 4. But this one, I guess it's better because I mean you can kind of get different answers. Like imagine if just 4 was true and the others were false. I guess there's kind of multiple ways to get just one answer choice correct. But anyways, all right. So we're going to go through all of these and figure out if they're true or false and then get our number at the end. So, statement one, when the limit at a certain point exists, it is always equal to f of that point, like its definition at that point. So, all right, so what is the difference between a limit and a definition? So a definition is just what the point is defined at. So if we put in a given x value, like x right here, the definition is just, f of x. That's all that is. The limit is a bit different though, because it's when you take, it's what value that x is approaching. Because sometimes they can mean different things. So the statement one is actually incorrect because sometimes they mean different things. Imagine if we have something like this, where we have a hole at a given point, but it's defined either above or below it. So it's defined down here, but the limit approaches the value up here. So those are two different things, so we know that one must be false. And I unfortunately have to erase all of this after every statement because I don't think there's a chance that I can fit all four of these very graphy questions onto one page, unfortunately. So statement two now, the value of a limit at a given point is always found by computing the definition at that point. That one's also wrong and false too because sometimes the definition does not exist, but the limit does. So sometimes you can find the limit by actually doing the limit instead of just doing the definition, which sometimes doesn't exist. In a case such as here, let's actually give what's a good function for this? Ooh, I know one. F of x equals absolute value of 1 over x. So that's a little different and weirder, but I think what that looks like is just this. Looks like that. This is the y-axis. This is the x-axis. That kind of looks like the engineering fountain. I accidentally just drew that just now. But anyways, you can see that the f of 0, which is right here, does not exist. Because if you were to plug in 0 here, you get 1 divided by 0, and that can't happen. You're dividing by 0. So we know that the function isn't defined at 0, but the limit as x approaches 0 does exist because it's approaching, looks like, infinity, positive infinity. So the limit does exist, and we found it out by actually doing the limit instead of taking the definition at that point, since it doesn't exist. So we know that 2 is also wrong. All right, let's see if we can get some, true answers here, because it's always worrying when you keep getting like the same type of answer right in a row. Like there should be like two, like one or two at least true ones here. It feels like it. Sometimes that won't be the case, but hopefully there's at least one. All right, statement 3. If the limit at a given point does not exist, then at least one of the one-sided limits at that point also does not exist. I think that one's false as well because another example that I can give, which is actually just the same as the last one, just without the absolute value, I think that looks like this off the top of my head. You can absolutely pull up Desmos if you want to, double check my work, but I think that's what 1 over x looks like. And you'll see that the limit as x approaches 0 does not exist because the left-sided limit and the right-sided limit are approaching different values. It looks like the left-sided limit is approaching negative infinity, and it looks like the right-sided limit is approaching positive infinity. So the regular limit does not exist, or I think they call it the two-sided limit, but obviously both of the one-sided limits do exist. We just found them. The left-sided limits and the right-sided limit, they both exist. So 3 also must be false. This is weird. Maybe they're all false. All right. I'm saying all of that as if I hadn't looked up the answer key beforehand. I don't know why I'm acting like that, but anyways. Statement 4. The limit as x approaches 0 from the right side of root x is the same as the limit as x approaches 0 from the left side at square root of x. Okay, this is a weird one because the definition of f of 0 of, the square root of 0 is just 0. So if we were to do f of x equals square root of 0, f of 0 just equals 0. So you'd think that both of these limits would also equal 0, since they're just 0 at the heart of it, and they equal each other. So this one is correct. But it's not, because they are one-sided limits. This one's from the right side, this one's from the left side. So if we were to graph this out, this is what it looks like. Kind of goes like that, and then off to infinity, y-axis and x-axis. And this is 0, 0 right at the start. So you'll see that it's defined. Here, let me draw that a little better, coming right out from that origin. F of 0, when you plug in x equals 0, you will get 0, because it's defined at that point, 0, comma 0. But let's see, the right-sided limit looks like it's approaching 0, but the left-sided limit, it's not really approaching anything, because the function isn't defined at all on the left side of the equation. It's not defined at all on the left of x equals 0. So the left-sided limit actually doesn't exist. So because of that, these don't equal each other, and 4 is also false. So we actually don't have any correct answers here. So yeah, that's just a bunch of limit problems and how they relate to their definitions at that point. And also, you had some one-sided limits as well. So as long as you're comfortable with all of that, questions like this should not be too bad. It's always, usually the problem with these questions is all four of these, individually aren't going to be too tough, but you have a higher chance of messing up one of them. And then when that happens, usually your answer ends up being wrong. So as long as you do your due diligence and you focus and you actually, you pay attention, realize what it's asking, and stay with it all the way through, you should be golden. Okay, question 9. This is the graph of f of x, whatever f of x is, we don't know, but that's its graph. Find the limit as x approaches 5 of the function here. All right, so this is x equals 5. This is it right here. We have a whole host of problems because A, they are approaching different values, the one-sided limits, they're approaching different values. B, the regular limit does not exist because both of the one-sided limits are approaching different values. And C, the actual definition at that point isn't equal to either of the one-sided limits. It's equal to 4. While the left-sided limit is approaching 6 and the right-sided limit is approaching 3. So I actually think I just answered the question in my explanation there, like bullet point B that I just said, because the left-sided limit and the right-sided limit are approaching different values, the two-sided limit doesn't exist, which this is. So we have our answer. I think this was just trying to mess you up by seeing that, oh, it's defined at 4 here, so our answer is 4, but that's not the case. Sometimes a function's definition and its limit are different things, even if it is defined at a given point. Question 10, a limit. So this is the point in these midterm ones where kind of the rest of the exams are all just limits. In fact, I think questions 10, 11, and 12 are all limits. So from here on out, we are just doing the limits, and more limits, which is fun. But all right, so limit as x approaches 0 of all this. So here's something that I actually completely forgot about when doing, I believe, spring 22 and fall 21's exams, is when you have limits that take the form of this, when you have a square root minus 4 or a square root plus 2 or plus 3 or whatever, when you have a square root like that, that is a telltale sign, that is a red flag that you can do this one weird thing where you multiply both sides by kind of this weird reciprocal thing. So it's 3x squared plus 16 plus 4, and then the same thing on the bottom, plus 16 plus 4. So that doesn't change anything since this fraction just equates out to 1. What this does is when you multiply everything out, it usually gets rid of any problems that you have in the denominator, because you'll see that we have the 0 here, and when you plug in 0 in the denominator, you'll be left with 0. That's dividing by 0. You can't really do that. So that's also why I didn't, instantly plug in 0, because it's obvious that we just get dividing by 0 at the end. I think in the two previous exams that I did, which is, again, the ones from 22 and 21, I did L'Hopital's rule, which I think would also work on this problem, but I think I remember that it's easier to do this method instead. So that's what I'm going to do, and we are going to get our answer. So when you multiply this out, when we start at the top, we will get, when we FOIL it like that, we'll get those first two terms, which are the same term, but they're square roots. So it's just going to be 3x squared plus 16 squared plus 16. And then what's cool about the way that we wrote this reciprocal is that the following two terms, the second term and the third term, the O and the I of the FOIL, they're going to cancel out because the O is going to be the square root plus 4, and the I is going to be the square root minus 4. So they cancel out, we can ignore it, and we just focus on the L, which is the negative 4 times positive 4, which is negative 16. And on the bottom, I'm not going to simplify it at all. I'm going to keep it as x squared times 3x squared plus 16 plus 4. And I'll get to the y in a minute. So on the top, we can simplify this. Plus 16 and minus 16, that is, they cancel each other out. And now we see we have an x squared on both the top and the bottom. So we can get rid of both of them, and we are just left with 3 all over this. And I believe now it's in a state where if we plug in 0, we won't be dividing by 0 anymore. When we go ahead and actually simplify it, we'll get an actual answer. We'll get one of these. So when we do that, we get 3 over 3 times 0 squared plus 16 plus 4. That equals 3 over just the square root of 16 plus 4. Square root of 16 is 4, and 4 plus 4 is 8. So our answer is 3/8. So yeah, I don't know why I blanked on this reciprocal trick so much. Just whenever you have this square root plus or minus a number form in either the numerator or the denominator, you can just multiply it by its reciprocal fraction thing. There's probably a name for it that I don't remember. But you just do that, and usually it will cancel out a bunch of things, and you can just go ahead and plug in the value that x is approaching, and you'll get your answer. Or you can do L'Hopital's rule, whichever you want to do. All right, question 11. We are almost done here with this whole exam. Evaluate the limit, another limit. So all right, looks like this one, it's a one-sided limit, so it's the limit as x approaches 1/5 from the right side, from the positive side. So I think this is going to end up being one of those number line limits, which I like to call them. I'll get to the y in a second, but first, what I recommend doing for every limit that you do is you just plug in the value that x is approaching into the function. So doing that, we get 1/5 over 10 times a fifth minus 2. That equals a fifth, not a half, a fifth, over, okay, 10 divided by 5 is 2, and 2 minus 2 is 0. So indeed, it is a form where it is, basically infinity. Whenever you have a, not a whole number, like just a regular number, like a real number on the top and then 0 on the bottom, when you're dividing by 0 like that, the answer is 99% of the time some form of infinity. It's either going to be positive infinity or negative infinity. So we can rule out everything else. Now to actually find which infinity it is, we can do the number line thing, which I don't know the name of. I kind of just make up all this stuff as I go. So the number line thing is where you make a number line, and right in the middle, you put that value that it asked. So 1/5, and then you define two other x values to the left and right of it. You want to use the closest values that you can that still make it pretty easy to compute those two values when you put them back into the top function, but you don't want them to be so far apart that it becomes sometimes when you do that, you have issues and you skip over a critical point, and that is bad news. So we don't want to do that. So we're going to try to pick two close enough values that still make this function like, valid, and it won't be equaling 0. We'll actually get a real answer out of it, a positive or a negative answer. So that is Sorry. That is easier said than done for this problem because I am tempted to put a 0 on the left here. That is the smallest integer we can use that is less, or that is the largest integer that we can use that is less than a fifth. But if we were to plug in 0, we get 0 over whatever, and that is equal to 0. That's not positive or negative. So we actually have to do something like 1/10 here instead. And on the right, I do think we can just use like 1. So we have a little salvation. So when we plug in 1/10 into this, we'll get 1/10 over 10 divided by 10 minus 2. That's equal to, uh, in these problems, you actually just care about the sign. You just care about the sign, the positive or the negativity at the end of it. So we're just going to put a plus on the top. And on the bottom, it's going to be 1 minus 2, which is negative. A positive divided by a negative is a negative. So what we're going to do is on the entire left side here, we're going to put a bunch of negative signs, a bunch of minus signs. And on the right, when we do the 1, when we plug in 1 into the top equation here, we should hopefully get something that is positive, and we'll go from there. If we don't get something that's positive, we know we messed something up when we skipped over a critical point. We'll go back, but hopefully we did things right. So plugging in 1, we get 1 over 10 times 1 minus 2. This is a positive over a 10 minus 2 is 8, which is positive. That is a positive final answer. So yes, we were right. This is all positives on the right. Now what we do now, this is the final step. Since we are trying to find our limit that is coming from the right side, this side, we know our answer is going to be positive infinity. So that's how you do these number line limits. Again, no idea what it's called. Probably some equation that, I don't know, Dr. Brown or Chen or someone explained to you, but I don't know what it is. But yeah, it's just where you first validate that the function evaluates to, infinity or negative infinity, something dividing by 0. And then you can go ahead and do that number line thing and then pick those two really close values, and you can figure out which side is negative and which side is positive. And then using those two, you can choose one that it said and get your answer if it's either going to be positive infinity or negative infinity. All right, question 12, the last limit and the last problem of this entire exam. So we have the limit as theta approaches 0 from the left side. That's a little different. And what's also really different is this absolute value here. That's a little uncommon, especially in limits. And yeah, usually it's kind of weird. You don't really know what to do at this point. But what you can remember is that usually what you do for absolute limits, generally in math, is you split up the function into two different functions. Usually it's one on the left side of the reflection and on the right side. Because you know that for what absolute limits does is if you have a function like y equals x, which is just a straight line, y equals absolute value of x is going to reflect it at, when it hits that x-axis there. All of these negative values, they become positive. So what you do is you split it up into two functions. This is really just two functions where it's the original, y equals x, and the reflection, which is y equals negative x. So we can go ahead and rewrite this original function into two functions where one on the left is negative sine theta over cosine whatever, I'll rewrite it later, and positive sine theta, what we had originally. So now is a good time to rewrite all of that. Cosine squared theta minus 1. Now, herein lies the rub. Because we are only asked to find the limit from the left side, the negative side, we're kind of only tasked with dealing the left side of this absolute value, this one. So we can kind of just ignore that one. Since we're not really asked to find the general limit, the two-sided limit, we don't have to worry about the right side of this absolute value. We can just worry about the left side, the negative sine theta one. And just like that, we've eliminated this absolute value, and we are just left with this more regular looking equation. So we're here at this point. Now it's just a matter of simplifying and figuring out what this limit equals, like a regular limit. I think what we can do actually is something that doesn't come up too often at this point in Calc 1 is the Pythagorean identity. It's different from the Pythagorean theorem. It states that sine squared theta plus cosine squared theta equals 1 every time for any value of theta. So what you can do and what you might see is that we can rearrange this a little bit. We can subtract sine squared and 1 from both sides, and we get cosine squared theta minus 1 equals negative sine squared theta. And hey, that is exactly what we have down here. We have a cosine squared theta minus 1. So we can go ahead and substitute that with negative sine squared theta. So negative sine theta over negative sine squared theta. Now at this point, we can cancel out the negatives and we can cancel out a sine from both the top and the bottom. We'll be left with 1 over sine of theta. And now at this point, remember this is still a limit as x approaches 0 from the left side. We still can't just plug in 0 yet. If we were to plug in 0, we get sine of 0 on the bottom, and sine of 0 is 0. So we can't do that because that would give us 1 over 0. And we also can't do L'Hopital's rule because L'Hopital's rule requires an indeterminate form, which is usually 0 over 0. So we can't do that. But what I think we can do is something that my TA actually did when I took this class, which is just kind of come up with these like kind of BS examples of like really, really small numbers and imagining what that would do on certain functions. So let me explain what that is. So if you were to take our unit circle, because we're dealing with, sines and stuff, so that's relevant. Take out a unit circle, this is 0 here, and remember that sine in this context, that is the length of this line right here. So if we have an arc that's that, sine would be the length of this line. So that's what sines are. So if we were to imagine a really, 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 really tiny negative number, something like negative 0.00001, which would be like that. Smaller than that. It would be right around there. I just enlarged it to show detail. That corresponding line length would also be a really, 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 really small negative number. It's negative because it's going down, and it's small because it's small. So we know that the bottom is going to be 1 over that negative really, really, really small number. And what that'll do is it'll make a really, really, really big negative number instead because it's on the denominator. When you divide by decimals, the numerator grows in size. So this is going to be a really, really, really big negative number instead. I think it's one more 0 there actually. So what that kind of tells us is that the closer we get towards that really, really small negative number being 0, this number is going to grow in size, or I guess shrink in size because it's negative, and it's probably going to approach negative infinity. So that is the cheesiest way I can come up with solving this problem. It's probably the one I would do on exams if I'm going to be honest. So maybe it works for you. Hope it does. But yeah, this was just one of those. This is a rare case of an absolute value in a limit, which is weird. But as long as you're comfortable with knowing what absolute values do and how they sort of just flip one of the signs, usually the left side, that it makes, its opposite version of itself, its negative version, you can usually deal with one of the sides and then go from there. You can find your limit. And with that, that is this whole exam. So it wasn't too bad, I think. I did this over 2 different days, as with all of the exams, but this one had like 3 days in the middle, I think. So I kind of forget what the first few questions were like, but this one was unique because question 1 wasn't a domain question. That's usually a given, but this time it was question 2. I've not yet had an exam that didn't have a domain problem on it, so at least it still had one. But yeah, it wasn't question 1, which was different. Graphing and functions inside functions, two inverses, which is different. Usually there's just one. Yeah, we had that one weird, like, what was it called? The unit circle. We had that weird unit circle question, which is different. Limits, graphing, and then a bunch of limits, as always. So, yeah, pretty Actually, this one in large was a little different than a typical midterm one, but still had a lot of the same topics. So it was good study material. So there you go. Fall, no wait, spring 2020 is now complete.